10 years. 10 years on and off, I've been working on this. Damn straight, I'm gonna make a busting video out of it. So about 7 years ago now, I saw a video from Veritasium, and my gut response was... no. Actually, it was more like... no. 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 You. But if you ask me for the details of that...
it's the smell.
It was a pretty ambiguous answer. Now, way back then, I really didn't have much resources beyond a few balloons and a camera. So I tried my best at the time to actually show that what was there wasn't actually correct, which did actually provoke an answer from Veritasium. But the problem always bugged me, right? That I didn't believe any of that. But more than that, I think that this is actually a really important phenomena that might actually end up determining whether you get life on a planet or not. And more recently, I actually took up the experiments again, but this time with much better kit. And now I can demonstrate absolutely that this is wrong.
I showed you that an electrically charged object can deflect a stream of water. But it is not due to the common explanation, the common reason which is given, which is that water is a polar molecule.
Actually, that's almost exactly how it works. With maybe the slight correction that it's not quite so much that water is a polar molecule, that it's got sort of positively charged bits and negatively charged bits in the form of the oxygen, which is more negatively charged, and the hydrogens, which are more positively charged, and overall the molecule being neutral, because carbon dioxide is also a fairly polar molecule like this, that the oxygens are quite negatively charged and the carbon is quite positively charged, whilst overall the whole thing is neutral. The critical thing about water is if you take the average position of the two positively charged hydrogens and the negative charge of the oxygen, they actually form a line called a dipole. And if you do exactly the same thing with carbon dioxide, well, the average position of the two negatively charged bits is exactly the position of the average positively charged bit. There's no fixed dipole. But of course, carbon dioxide isn't a liquid, well, under most sensible conditions. But what if we had a liquid like carbon dioxide, where it's actually quite polar, but has no net dipole? Do you think that would exhibit this sort of behavior?
So what really is causing this water to be attracted towards the cup? Well, it is charges, but it is ions. It is dissolved ions in the water. There will be some OH ions, some H+ ions, and there will also be some other impurity ions in the water. So what happens when you hold this negatively charged cup up against the water stream is it will repel the negative charges, the negative ions in the water, some of which will go back up into the tap.
Now that is a testable claim.
And that means the water coming down will be slightly positively charged.
And that is a testable claim.
And once it breaks up into droplets, those droplets have a positive charge that they can't get rid of. So now those positive droplets are attracted to the negatively charged cup. And you can see those droplets swirling around the cup because they are so attracted to it.
And that is a testable claim.
So this is not actually a very good demonstration of the polar nature of water. Even non-polar substances with some ions dissolved in them will deflect in exactly this way. So this is actually showing us that water droplets are charged. They are charged by induction, and it is not due to the polar nature of water that they are attracted to electrically charged objects.
Now, it's always a dangerous point in research when you make predictions, because this is when people can demonstrate that you're absolutely wrong. They can do the experiment of how you say it behaves, and if that's not how it behaves, then you're wrong. Especially important to have actually checked that sort of stuff out before you actually said, all the other people have got it wrong, and this is actually the way it is. So let's see in detail how those experiments work out in reality. So in order to understand this, you need to understand the tools of the trade, which with the exception of the really important polyethylene cup, I'm not kidding you, this turns out to be really important for all of this, is all Victorian era science. So here we have the Wimshurst machine. This thing is one of these guys who generates like tens of thousands of volts, and that bang that you hear there is a spark going through 5 centimeters of air. That's like 50,000 volts, something like that. This is the Wimshurst machine up close. I've gone over to the more open mic so you can actually get a real feel for the handle cranking and the size of the sparks. So the more the gap is, the smaller the gap, the more frequent the sparks. The bigger the gap, the less frequent the sparks, and as you get further apart you get up to maximum voltage. So this is now maximum voltage, and you know that because if I now move it back in, we'll get one last big ass spark. These work by having an excess of electrons on one probe and a deficit of them on the other. And obviously once it gets enough of a excess of electrons on one side and a deficit of them on the other, you get the big ass spark, and that's it. Now those are all held on metal. So if I take a nice little piece of metal like this and I charge up my Wimshurst machine and I touch that on one of the probes, this is still charged up at like 10,000 volts, right? This now has inherited the charge that was on there, or it's all equilibrated. So I can actually carry little bits of positive or negative charge around depending on which probe like that I touch it on. Now this is where polyethylene becomes hugely important, because polyethylene won't do that. I can touch this on this probe as much as I want and this thing will never pick up any charge, which I can demonstrate to you in wonderful graphic detail later using the last piece of Victorian era science here, which is the gold leaf electroscope. Now the way the gold leaf electroscope works is if there's anything that's charged nearby this, it induces a charge on the top plate here, and the gold leaf, because everything is positively charged down there, it all repels from each other, the gold leaf sort of swings up. Good. So demo number one is I'm going to charge up my Wimshurst machine and touch that on one of the probes, and you should see that the gold leaf here is super responsive to the electric field coming off this charged disc of metal here. And if I touch it on the other probe, you'll see that it's exactly the same. So this is a great way of detecting where charge is. Okay, so the reason polyethylene is so important is because we can see there's no charge on it at the moment. And if I charge up the Wimshurst machine, you will find even if I touch this onto the probe, you don't get any electrons sticking to the polyethylene. Now, what if I add some water to this? So now you can see that I've got my water in a polyethylene cup, and there is essentially no charge on it. And now I'm going to get my metal disc, which I'm going to charge up to several thousand volts on the Wimshurst machine. And this is probably even, this is too much. Let's see. Yeah, see, this might trash my gold leaf electroscope here, but I'm going to just touch that on the surface of the water, and we'll see what happens. And you see that it's stuck way up top there, and we know that's actually now the charge is actually stuck in the water. Yeah, and we know it's stuck in the water because if I pour it out, you'll find that all of a sudden the cup has no charge left on it. So this turns out to be really important for everything here. Now you might recall that I said polyethylene can't hold charge, which is kind of true. It can't hold excess or deficits of electrons on its own. Now, you can't get them in the surface. Now what you're looking at there is when the metal is touched onto the water's surface, some of the electrons go into the water where they chemically react very quickly to form hydroxide ions. Now, polyethylene, of course, can't do that. This is why if I put my polyethylene on here, I get no charge. And if I touch it onto the charge probe, I again get no charge transfer. However, if I rub it on my hair, Now all of a sudden you find that this thing has huge amounts of charge on it. And this charge can't be simply earthed by touching it. And this is because what I've done here is I've rubbed some grease from my hair onto this, which has either given it a positive or negative charge. I'm never entirely sure which, but it doesn't matter. It's stuck there for an extended period of time and it can't easily be earthed away. Okay, the reason this is so important is it now gives you the absolute ability to test the Veritasium explanation.
And once it breaks up into droplets, those droplets have a positive charge that they can't get rid of. So now those positive droplets are attracted to the negatively charged cup. And you can see those droplets swirling around the cup because they are so attracted to it.
Yeah, all those positive charges falling down, they would really charge up a gold leaf electroscope.
So I now have my stream of water coming out of an entirely polyethylene kit, and you'll see there is no charge whatsoever on this. So if Veritasium is correct and the stream bends because it's being attracted with the ions and there are actually positively charged ions coming out of the bottom, then if I bring up a charged object here and it bends the stream, we should see an accumulation of charge in the bottom. So let's do that. And we charge it up and we find that even as we bend the stream, there is no charge build-up at the bottom. None. So that shows you that you can bend the stream without having a surplus of ions coming out of the bottom. So fundamentally, what he was saying is wrong. However, not entirely wrong. So if I actually now bring this from the point where I'm bending the stream and I'm getting no charging, and I move it now up to this part in the middle here where I'm not actually bending the stream at all, but look, it's charging up, it's charging up. And I take it away again and it loses its charge, and I move it back again and it charges up, and I take it away and it discharges.
It's a fat cop.
Even more funky, what if I do exactly the same thing but up at the top here? And you'll find that now it charges up, and I take it away and it discharges, and I put it there and it charges up. And what's more, if I bring it quickly down, it goes down and then it comes up again. And if I move it up, it goes down and then it comes up again. So what Veritasium was saying is true in part, in that you do actually get some separation of charge here, but you can show that that's not what's bending the streams here. So I can demonstrate absolutely that the reason that this is being attracted isn't because of the ions. Let's say this is negatively charged, and Veritasium's explanation is indeed correct, that this is actually being attracted because the negative charge is attracting lots of positive ions here, and that's what's causing the charging, and it's what's causing the stream to be attracted. Well, the same is true if I do it up here, that now I've got all the positive charged waters up, or the positive charged ions in the water up here, and negative charged ions here. That means that if I were to get something else that is also negatively charged, and I charge up the stream, I know there are now negative ions coming out the bottom. I know this is negatively charged, so it should be repelled, and it's still strongly attracted, which shows that the majority of the reason why you're bending the stream isn't because of the charge on the ions. Can I not force its hand here? Can I not make the water negatively charged enough that it's actually repelled from a negatively charged object? And the answer is, maybe if I had something that could generate tens of thousands of volts. Now there's a really important distinction with water here. There's the bit where it's a continuous stream. At that point you can still in principle move charge around because it's all a contiguous body. However, once it breaks into droplets, those droplets will inherit whatever the properties of the end of the tip were, presumably.
And critically, this is what that stream looks like, filmed at about 20,000 frames per second. So as we come down the stream, you'll find there's a bit where it actually, these are fairly small droplets, bear in mind, but there's a relatively short time when you go from laminar flow to broken into droplets. And once you're broken into droplets, there's actually, it's a remarkably constant stream with fairly constant distances between them.
So if I've got lots of positive charge being dumped in there by my Wimshurst machine, then the droplets coming off the bottom will be positively charged. And if I can charge up this and it's also positively charged, then it should be repelled from those droplets to the bottom. And logically, it must also, because the droplets are positively charged, if they're repelled away, then the stream must be repelled away as well. Right? Okay, so let's get our stream going. And we can charge it up to tens of thousands of volts. And we know it's at tens of thousands of volts because all of a sudden it goes from a stream to a remarkably impressive spray that goes absolutely everywhere. And as the charge bleeds away, it slowly comes back.
And this is what it looks like when it's fully charged up, doing that exact same thing. So let's blow that up to the same amount as the other one. So now we're blown up all the way in like we were last time. And as we come down, you find that this bit where you go from laminar flow to droplets, all of a sudden, the droplets are different in size and they behave very differently. It's almost as if electric fields can cause differences in surface tension. Anyway, so this is the sort of maximum sort of repulsion that you can get between all of these droplets. And this is what they look like side by side.
So we've got a lot of, let's say, positive charge on this. And let's say I've got a lot of positive charge on that. That means that this should be, and it is, it's repelled. It's repelled from my, so let's try it again. Repelled, and it is attracted up here. So, and now as the charge goes away, it's super attracted, and it's still repelled at the bottom, attracted at the top. And to show that really is what's going on, I can overwhelm this. So at the moment, it's attracted. Now let me put loads of charge on this, and all of a sudden it goes from attracted to repelled. So you see what's going on. That's good, beautiful. Now, I'm going to charge up my piece of plastic here, and as you see, strongly attracted. But interestingly enough, I do it down at the bottom here, neither attracted nor repelled. Attracted, not attracted. But now if I charge it up with a Wimshurst machine, now it's repelled at the bottom. That means I've got whatever the charge on this, the charge on the stream is the same, so they're being repelled. So if they're the same charge down there, then they must be the same charge up here as well. And no, it's attracted up here. Let's get that charge up again. Strongly attracted. Even though it's strongly repelled, strongly attracted. Alright. So, and you know, if I really charge it up, you'll actually get it repelled up at the top as well. And charge that up strongly as well there. So yeah, these weird things where it's sort of attracted. Now I can make it repelled. So, but it's only when it's fully charged up on the Wimshurst machine, such that the water is doing some fairly funky stuff. If I really charge it up, then yeah, at that point with the water at like 10,000 volts, then the Veritasium explanation holds true. Whereas for this bit, absolutely not. This is strongly attracted even when it's negatively charged at the bottom there. Well, let's do some quick experiments on, say, some super salty water, like that one there, has a really concentrated salt solution, and this one, which is one of the purest of waters that you can actually get. So, you know, ultra pure water has very little in the way of ions in it, yet it's still super responsive to my electric field. Okay, so now we can in situ swap that over from what was really pure water to really salty water to see if that has any difference at all on this. So let's go for the really salty water. And now, it really doesn't have any difference in how responsive it is to the electric field, which is like, that's a little weird. Okay, so it doesn't really make any difference if you've got ultra pure water or not. But what if you had a selection of different solvents like acetonitrile, dioxane, butanol, dichloromethane, hexane, tetrahydrofuran, dimethyl formamide, and formamide? What do you think their responses is going to be on this exact same test? Okay, acetonitrile is the first one up. And acetonitrile is running. And we find he is super responsive, maybe even more so, to the electric field. It's like, Next up, we have dimethyl formamide. And how does dimethyl formamide go? Again, super responsive. It's like there's almost no difference between any of these. So what the hell's going on there then? Next up is formamide. And how does formamide roll? Just as responsive. It's crazy. It's like there's almost no difference between any of them. Butanol. And how responsive is butanol? Why, almost exactly as responsive as everything else. And maybe more so. Look at the spray coming off the bottom of that. That's quite impressive. Dichloromethane. Oh, big flow on this one. And dichloromethane, the dense halogenated solvent, is also strongly, look at the spray at the bottom, strongly perturbed by the electric field. Maybe a little less so, but maybe that's just because this is rotated a little. Yeah, or maybe I'm just not charged up quite. Or maybe it's just a higher flow rate, I don't know. Tetrahydrofuran goes in easy. Super. And tetrahydrofuran, also crazy responsive. It's like, there's almost no difference between any of these. Next up, dioxane. And dioxane, we charge it up. And there's nothing. Nothing. They charge it all the way up. And it's like, what the hell? No. Dioxane, what the hell's your problem? Why aren't you working, dioxane? I know, let's put a little bit of butanol in the top there to see if that actually helps spice things up a little. Butanol worked fine, and we find that a little bit, oh, look at that now. Crazy. Last but not least, hexane. And with hexane, we charge ourselves up and nothing. Nothing. Absolutely nothing. Okay, let's pull that same stunt that we did before and put just a little bit of butanol in there just to see, and let's do it in real time. Nothing. Oh, well, how's that for an effect then?
So it seems to be a pretty binary test. It's either attracted into the field by an almost constant amount, or you get nothing. And the criterion for the ones that do and the ones that don't is simple. If you don't have a dipole, you don't get attracted into the field. So dioxane, yes, it's dioxane, not dioxane, not a solvent I use that often, is actually quite polar, but has a tiny dipole. In fact, it's not far off what I suggested earlier as basically liquid carbon dioxide, polar but with no dipole. So when we're running computer simulations of these things, we model this by having partial charges on the atoms. So water is basically minus 0.8 on the oxygen, plus 0.4 on the hydrogens. And it's a bent molecule, so you get a nice big dipole. Carbon dioxide's not far off that in the partial charges, and it's plus 0.6 on the carbon and minus 0.3 on the oxygens. And dioxane is minus 0.4 on the oxygens and almost a homogeneously slightly positive charge for the rest of the molecule. And the partial charges for the other molecule that gave no deflection in this field, which was hexane, basically has 0 charges on the whole molecule. Now, the stunning thing is, the solvents that I chose here had a huge spectrum of properties in dielectric constants, densities, surface tensions, and yet almost none of it seems to make any difference. You've got a dipole, you all behave the same. Now, you got to be a little careful here, because the charges that we're talking here are so minuscule. My ultra pure water here has about 1 molecule in 10 million being an ion from the auto dissociation. So about 1 part in 10 million is going to be a hydroxonium, 1 part in 10 million is going to be a hydroxide, that sort of thing. And there's an equal number of both of them. So overall, it's electroneutral. And the charges that you're looking at for these static charges here are about 1 million times lower than that. So there really aren't any analytical techniques that can track down purities this low. But at these sorts of levels, you expect all of the solvents, including dioxane and hexane, to have this sort of level of ionic contaminants. In fact, maybe the only place where we can get a totally pure solvent would be in a computer simulation, in a molecular dynamics simulation. Well, there is an interesting question. In molecular dynamics, do liquids with dipoles but no ions behave differently in an electric field to liquids with no dipoles?
So what happens when you hold this negatively charged cup up against the water stream is it will repel the negative charges, the negative ions in the water, some of which will go back up into the tap.
So yeah, there's a whole bunch of sarcastic things you could do, like, if this piece of paper is attracted to a charged up cup, does that mean that the ions are going back up into the tap?
So this is actually showing us that water droplets are charged. They are charged by induction, and it is not due to the polar nature of water that they are attracted to electrically charged objects. Now you know.
And it's like, I'm not so sure that's true. Okay, so what I can show you is if I charge it up to full, it's attractive, and we can just about get it to be repulsive with a lot of effort. Yeah, just about repulsive. Now, if we swap the probe on the Wimshurst machine over, carefully, and now we try that again, and we find that now it's super attracted. So, whereas previously full charge would just about bend the stream, now it goes absolutely ballistic in a way that it never did before. So you can only get that if there are at least 2 factors in play. Now you might recall I said polyethylene was absolutely key in all of this. So all of this is polyethylene or polypropylene. It's basically the same stuff, which is frozen hexane. It's a much longer version of hexane, which is essentially solid. You can just about melt it. But hexane was impervious to our most powerful electric field. Hexane, we charge ourselves up and nothing. Nothing. And hot glue, and then the syringes are made of polypropylene. So what would happen if I were to get a syringe, melt it and draw down a really thin fibre? That would be like a frozen jet of hexane. And what if I were to then put some water into that little thin tube? Would that then be attracted into the electric field? So let's take a look. Right, so we're at some point going to use the syringe to pull up some extra water into all of this. In the meanwhile, we're just going to clamp that in there. Polyethylene turns out melts at about 150. So you can actually quite happily melt polyethylene like so. And now we're just going to use that to draw down a nice thin fibre. Super. I'm going to give that a second or two to cool. In the meantime, we can cut it probably about here somewhere. And this should have no attraction to our the electric field, and indeed it doesn't, because it's essentially a frozen stream of hexane. So now let's suck a little bit of water up into there and see what that does for us. And blow some bubbles, that's good. And a little bit of sucking. There we go, super. So the water level is just here. So that bit's got water in.
So this is going to be another nice little test of the Veritasium explanation, where you need the ions to go back up into the tap in order to create an overall positively charged stream, in order to be sucked in to the electric field. So if Veritasium is right, there is no way this can actually be attracted into the electric field.
The water level is just here. So that bit's got water in. And now, oh, starting to twitch. You see, even just a little bit of water in there, starting to twitch. No matter which side I come from, starts to twitch. I'll suck up a continuous stream of water up to about there. That's good. The water goes up to there now. And oh, we're super attracted to this. Yeah. Super attracted. Yeah. Cool.
And believe me, I could go on and on, but I figure I'll draw a line under it there. Hopefully, I've done enough to convince you that this is a lot more entertainingly complex than first meets the eye. So what is my angle on all of this? Well, like I said, I think there's a lot more important stuff going on here. Like, do you actually need a dipole for lightning? So could you get lightning on a planet where the atmosphere is, say, mostly carbon dioxide, like Venus or Mars? Because lightning is a big driver in prebiotic chemical synthesis. And believe it or not, lightning is not terribly well understood either. So many thanks to all those who support this channel through Patreon. Drop a thumbs up on the video if you thought it was interesting. And if you really want to get a Wimshurst machine or the gold leaf electroscope, I'll leave some Amazon affiliate links below. And thanks for watching.